start recording. And I'm going to put up one slide while I make the caveats for this talk. So as you probably know, I'm giving this talk in order to continue the streak of having talks every week, but this talk will be extremely improvisational. So what I'm going to try to do is jump around between a few PDFs I have open and mash up some talks that I gave in the past that are vaguely related. So since it's so improvisational, please feel free to interrupt at any time. If you want to talk about something that's more or less interesting, I'm happy to shift away from like what I was going to discuss and discuss that instead. So you can kind of choose your own adventure, so to speak. And the other caveat is, unlike the gauge theory talk, this is not something I'm really much of an expert in. I've never written a paper on Langlands or anything. I was interested in learning about it because Ed Witten has a paper related to geometric Langlands and string theory. But because I'm one, not an expert, and two, the last time I gave this talk was years ago, I'm very likely to either misremember or say something incorrect. So I invite you to call me out or ask for clarification or anything, and we can either hop over to Wikipedia or a textbook to check if I say anything incorrect, which will certainly happen. But okay, with those caveats out of the way, what's the general story I want to tell you about today? So I want to give you a caricature for what the Langlands program is. The Langlands program is this, as you may have heard, is very ambitious piece of or research agenda in mathematics that connects a bunch of disparate fields. So I'll tell you mostly about a connection between harmonic analysis and number theory. That's what I'll try to illuminate. The connection to geometry is a bit more difficult to describe, but just in a nutshell, what we'll focus on for this picture is solving a given equation over different fields and seeing how those solutions in different fields are related. So for a very concrete example, if we look at a cubic like this, so some equation in two variables, whenever you solve an equation, you have to say, okay, what are the solutions allowed to be? If the solutions are allowed to be complex numbers, then the solutions to these things form what's called a Riemann surface, which is a subset of Cn for some n. And that's a geometrical object with some fundamental group. So you can study the fundamental group of that surface. That's a geometrical question. A very different number theoretic question is to say, okay, well, I don't want these numbers to be complex anymore. I want to say they take values in Fp for some prime p, so a finite field. If you count the number of solutions, you get a series of integers a sub p, which will turn out to contain all of the same data. They're in one-to-one correspondence with the fundamental group in picture 1, and also with something else, the symmetry group of a function. In this case, for this particular cubic, it will turn out to be a modular form, but more generally, they can be automorphic forms or automorphic functions. And as it turns out, the AP that are contained in the solutions to this thing mod in fields, finite fields mod p, also is in one-to-one correspondence with these functions with particular properties. So that's the caricature, that these three different questions, counting some excess solutions to an equation in a finite field, contains the same data as the fundamental group of the solutions over the complex numbers, which contains the same information as a particular function, in this case a modular function. And just for one piece of motivation, I will, if you think that this seems all kind of abstract or, well, it's certainly abstract, but if you think this is kind of just mental masturbation, that we're just pushing around equivalent definitions, this is an extremely useful correspondence because, for instance, the main tool which was used to prove Fermat's last theorem was exactly this correspondence. So if you don't know, I'll just sketch it very quickly for you. The proof of Fermat's last theorem is basically the following, that you take, Fermat's last theorem is saying there's solutions to some polynomial like x to the n, y to the n, z to the n, or whatever. What you do is you assume by way of contradiction that there is such a solution. You use that solution to construct a particular cubic, similar to this cubic. Then you show that the solutions, these a sub p, which are solutions to that cubic in Fp, you show that those a sub p descending from this cubic cannot be related to a modular form, which is a type of function, again, in this third part, cannot be related to a modular form. And then you use something called this Shimura-Taniyama-Wei conjecture, which you may have heard of, which was eventually proven. But this conjecture tells you there's a one-to-one correspondence between these sets of AP for these cubics and modular forms. So then you apply, I guess I'll write STW for this Shimura-Taniyama-Wei conjecture. You apply this conjecture, which tells you there's a one-to-one correspondence between these AP and the modular forms. So then you've reached a contradiction because you say, okay, these AP for this cubic, you show they cannot be associated with the modular form, and that contradicts this conjecture, which was eventually proven, I think, by Ken Rivet. And that's the proof of Fermat's theorem. So this is extremely powerful if you have this correspondence between these three pieces, because it allows you to kind of import results from different pieces of mathematics and use them as you see fit. But okay, so that's the motivation. What I'd like to do now is take a little detour and focus mostly on number 3 here. What are these, well, automorphic functions, but in particular modular forms? So I'll jump over to a different set of slides to go through kind of a lightning explanation of what are modular forms, which are a particular case of automorphic forms, where do they come from, and I'll show some connections to string theory and even some of my own research. Eventually I'll jump over to a TT bar paper. But before I do that, any questions, comments, concerns, or death threats about this big picture Langlands motivation? I have 2 screens, so I'll try to watch the Math Talk discussion channel in case anyone posts anything. But okay, if there's no questions for now, let me go over to the modular forms. So we want to understand what are modular forms because they are in this simplest example of Langlands. So this other talk has 3 acts, of which we can kind of jump around or speed run if you're more or less interested in some parts. But the first part is going to build up to what a modular form is by talking about symmetries of functions, and then I'll tell you what the modular group is, which is a very important object in string theory and other pieces of mathematics, and then I'll finally tell you what a modular form is, more precisely. Okay, so how do we motivate this? As always, before giving a definition, I think it's important that I convince you that it's doing something interesting, so it's worth your time to listen. So let's think about functions that have certain symmetries first, because symmetry is always a nice thing to study. So if f of z is some function, which is defined on a domain, some subset of the complex plane, and G is some group of transformations that act on the plane, so G is a group with an action on C, then we say that f is symmetric under the action of the group G in kind of the obvious way that you would think, if the function evaluated on the action of G on a point Z is the same as the function f evaluated on the untransformed point Z for any G in the group. So it's just saying if you act with the group action, the function doesn't care. It spits out the same value before the action as after the action. Very natural definition, but let's think about it as a stupid concrete example, like translation invariance. So thought of as a complex function, f of z is sine z. This is pretty obviously invariant under a particular shift. If I just map z onto z plus 2 pi n for any n, this is just shifting the sine function, and it doesn't affect the output. So if we say, okay, what symmetry group does that mean sine z is invariant under? Well, it's the group of all those translations. So it's the set of G sub n, where G sub n is the map that, this is a kind of bad notation, but G sub n is the map that just shifts you from z. I guess I probably should have put a z there. Gn maps you from z to z plus 2 pi n for any n. That's a group. It's a pretty simple group. It has the identity element. Of course, you can shift when n is 0, which does nothing. You can compose, where it just adds the n and the n for 2 different guys, and the inverse is just shifting by minus n. So this is a group, and sine z is invariant under that group of symmetries. Okay, nothing magical there. It's high school trigonometry, basically. Here's another example. This ties in with our last talk, the gauge theory talk, the U1 gauge theory talk. So here's a function. Take a complex number and spit out its norm squared, its absolute value squared, if you like. So that function has a symmetry because basically all it cares about, if you think in complex coordinates, all this function cares about is r. If I have a point z sitting at r, this function is basically f of z is r squared, right? It's just telling you the distance from the origin in the complex plane. And clearly such a function does not care if I rotate this guy around by any theta. So here there's a group of symmetries. This is called U1. We discussed this in the last talk. U1 is the group of symmetries of the circle. Its elements rotate a complex number z to e to the I theta z, where theta is some phase, some angle. So this is the circle group. This was a key ingredient when we were doing electromagnetism, because in that case we were thinking of these rotations as changing the phase of the electron, right? And we wanted all of our physical quantities to be invariant under that translation. So this function clearly has that symmetry, because if we do this rotating, you get an e to the I theta and an e to the minus I theta, so they go away, and you're left with the old f of z. Good, another simple function with a very simple symmetry group. So why are these sorts of symmetries useful? Well, there's a very common strategy in mathematics that if you want to symmetrize something, if you have a function f of z, which is not invariant under some, in this case, a discrete group, but you can generalize this to continuous groups using a Haar measure, you can create a new function that does have the desired symmetry. So you make a new function f tilde, and all you do is you add all of the functions with elements of g acting on them. This is why I wanted it to be discrete, so I could have some finite sum or maybe an infinite sum that converges or something. But you just add up f acting on all of the g translates, if you like, of a point z. And now we can prove immediately that this new function f tilde does have the desired symmetry group. Why is that? Well, if I take any element h in the group and I evaluate f tilde on h of z, well, by definition, that's this sum over the g's of f on g of h of z. But as we know, if you act on the left by any group element in a group, it's just some automorphism of the group in some, right? It permutes the elements around. So I can define a new group element g prime, which is just g composed with h. And then because this left action is an automorphism, this sum is the same as the old sum, right? We're still summing over all the elements of g, but in a different order, right? So this is still f tilde acting on the untransformed point z, right? So that's just this thing that if you act on the left, it just moves around your group elements. Okay, we can use this to prove something nice. I'll do an actual, oh wait, I think the proof is 2 slides away, okay. First, an example of the averaging before the proof. So again, we said you can average to get a function with some nice symmetry group. Here's an example. If you want to give a function translation symmetry, right? For instance, before we had the sine function, which does have translation symmetry. Oops, yeah, here the sine function does have translation symmetry. It's invariant under this group G. If you have a function that does not have that property, but you would like to make a function with that property out of it, you just do what we just said. You define the f tilde to be the sum of all of the translates. In this case, I'm not doing by 2 pi n, I'm just doing by n for simplicity. And if you can show that that sum converges, then you get a periodic function out of it, right? You get a periodic function or a function that's g symmetric under this g, which is the group of translations, for the same reason we just said, right? Because if I evaluate, for instance, f tilde on z plus 1, well, that's this sum of f evaluated on the z plus n plus 1s, but I could just define this n plus 1 as an n prime, and then the range of summation is still over z, so I get my f tilde out. So I can make a periodic function out of it, and then since every periodic function has a Fourier series, you can extract some Fourier coefficients, some CMs, out of that guy after making it symmetric. Good, so this is just an example of using the averaging to get some sort of periodic function that might have some nice properties. Another useful thing that you can use averaging to do is to prove this useful formula about something called Poisson Resummation. So if you haven't seen this, it's basically the statement that you can trade a function for its Fourier transform inside a sum. So to be more precise, if f is a function on R but that spits out complex numbers, and it has a smooth Fourier transform, f tilde, to have a smooth Fourier transform, that basically means that the original function f has certain decay properties at infinity. Then the conclusion is that the sum over all integers of f of n is the same as the sum over all integers of f hat, where f hat is the Fourier transform. So I can trade the function for its transform inside a sum. Okay, what's the proof? Well, we do basically what I just described on the past couple slides. We say, okay, I'm going to define a new function capital F by taking my old function f. Remember, f is not assumed to be periodic. It just has a Fourier transform. But I make a periodic function by averaging over the translates. I add up f at x plus n for all the n's. This guy is now periodic by construction. And as I just argued on the previous slide, if you do this procedure to get a periodic function, that guy has some Fourier coefficients now. It has a Fourier series, not just a Fourier transform. It has a Fourier series because it's periodic. The Fourier series, well, it has some coefficients. We do the usual, calculus trick. What's it called? Fourier's trick or something, where to get the coefficient, you just integrate and use orthogonality. So if you want to get the kth Fourier coefficient, what do? Well, okay, you just integrate from 0 to 1 this function capital F, which I've put in here, multiplied against a particular phase that picks out the desired coefficient, right? Because by orthogonality, if I multiply by this phase, it's going to pick out the coefficient that I want, the kth one. Okay, so how do I evaluate that integral? Well, I'm a physicist, so I will exchange summation and integration without apology, but this can actually be proved that this is legitimate because of the smoothness of the Fourier transform. You can exchange these. You exchange these, and the sum over n and z using periodicity, well, by periodicity, integrating from 0 to 1 doesn't matter if I go from 0 to 1 or n to n plus 1, because this guy is periodic. So I just change the bounds of my integration. And then that, by definition, if you add up over all n and z, the integrals from n to n plus 1, well, that's just now the integral over the whole real line, right? I've chopped up the real line into integer buckets, and then integrated, or adding them all up is just integrating over the entire real line, which is this here. And then this is, by definition, the Fourier transform evaluated at k, right? This is the definition of the Fourier transform f hat. So what have I done? This little manipulation is just telling me that the Fourier coefficients of capital F are just the Fourier transform evaluated at the kth integer. Right, so we can just write that in this way, which is saying capital F is a Fourier series with these coefficients. And then now we're basically done. To get the result that we wanted to prove, you take this relationship and set x equal to 0, just to kill off this phase, because e to the 0 is 1, and you get the desired result. So this is nice. This Poisson Resummation lets us, if you know a Fourier transform, you can just freely exchange them. Okay, so when I originally wrote this talk, I had a challenge baked in. So I don't know if it's considered bad etiquette to ask you to solve this, but maybe just think about this for one moment and see, can we use this Poisson Resummation theorem to prove this particular result, where the result is, if you define a function t of a, that's the sum over the integers of e to the minus a pi n squared, which turns out to be an interesting function. It's kind of related to these Jacobi's. How would you prove that t, this function t evaluated at 1 over a, is root a times t evaluated at a? Think for a moment and unmute if you have a proposal.
I guess I'll say it. So I think the way to do this is, we know from the formulae before that because f of x is, when f of x is eaten in negative AP x squared, then the sum over it is the same as the sum over its Fourier transform, which we know is f of x of 1 over a inter divided by square root a. And we plug it in and we can multiply square root a over.
Yeah, perfect. That's right. So indeed, if you didn't catch it, what he said was you think of this as, this is a sum of some function f of x is e to the minus ax squared under the sum, and then we use the theorem, the Poisson Resummation theorem, and say, look, I can replace this by its Fourier transform, which I've nicely written for you here. It's just a Gaussian integral to prove this, so it was kind of a trivial step. So then you say, look, I can replace this with the sum, say, over m and z of this Fourier transform guy, which is 1 over root a e to the minus pi k squared over a. And then this thing, since this has a 1 over a sitting in the place where a was originally, this is essentially, well, not essentially, it is. This is 1 over root a times t of 1 over a, right? Good. So it's just an algebra step. Then indeed, you multiply both sides by root a, and it proves this result. Good. So this is nice. I introduced this because this will turn out to be related to one of the generators of the modular group, the S transformation. So keep in the back of your head this picture of, a function that has a nice property when you invert its argument, right? This is a very special property. Usually if you evaluate a function at 1 over an argument, it's generally not, like, it has no relation to the function itself. So this is a very nice property, which will turn out to be related to the modular group. Good. All right, I'll forge on and then stop for questions at the end of this act. So you might want to generalize this a little bit. You might say, okay, sine z was very nice because it was periodic in one direction. What if a function were periodic in 2 different directions, right? Because this whole picture we're taking place in the complex plane, right? So you can imagine being periodic in both, say the x direction or the real direction, and in the imaginary direction, the y direction. Or more generally, it doesn't necessarily have to be x and y. You could find 2 kind of complex periods, if you like. So pick two directions in the complex plane and say, I would like my function to be invariant if I shift by an integer multiple of either this first period or an integer multiple of this second period. And if that's true, it follows that you can, of course, shift by any linear combination, integer valued linear combination of the two guys. I don't know what happened to my LaTeX there. I think that should be Z. So if you have such a function that's doubly periodic, there's an equivalent way to say this. You say, look, I have a lattice of points. The lattice is just all of these shifts. It's the set of all lambda that are integer combinations of omega 1 and omega 2. And that means the function should be invariant under shifting by any lattice point, right? It's shifting by any lambda that's of the form that we wrote up here. That's a doubly periodic function. And if you think for a moment geometrically about this lattice, you'll realize that such a doubly periodic function, since there's basically a domain, a little region inside of one of these kind of lattice copies, if you will, there's a little domain where the behavior of the function inside that domain determines the values of the function everywhere else, because it just translates. So you think, okay, my function, here's the lattice with omega 1 and omega 2. If I know the values of the function everywhere inside this little parallelogram, this little lattice, fundamental cell, if you like, if I know the values of the function everywhere in here, then I know the values of the function everywhere in the plane. Because if I want to know it, for instance, here, that's related by a lattice vector to the value of the function here, right? There's a lattice vector that points from there to there. So if I know the values of the function inside the fundamental domain, I know it everywhere. But if you know topology, you realize, oh, this parallelogram is basically a torus if I identify the sides, right? Because, of course, the lattice vectors also connect the sides of the parallelogram. So by this double periodicity, that means the value of the function on one side is identified with the value of the function on the other side. So if I glue those together, I basically get a torus, right? So the claim is that any doubly periodic function in the complex plane is exactly equivalent to a function defined on the torus, because I just take its fundamental domain or unit cell, and the sides have to be identified. So I think of this topologically as a torus, and then now I have a function that takes in a point on the torus, and then spits out some, z, spits out f of z given a z on the torus. Okay, that's very nice. So let me pause, and if there are questions, or if anyone wants me to, if you're getting bored with this subject and want me to, to jump to something else, now's a good time to let me know. Or if there's any thoughts about this first act about functions on the torus, ask now.
That thing about the like that sum of like those like exponentials, that challenge thing, that thing,
Good.
that looked a lot like what's it called, the theta function? I think that's what it's called.
Which were the Jacobi theta, you said?
Yeah, something like that, and like the
I think it's exactly one of them, but go on. Yeah.
I don't know if it's probably related, but I don't know how.
Yeah, it's definitely related. I think it's the usual Jacobi theta has the n squared piece and then another 2 pi I n z. So I think this capital T I used is you define, usually when you discuss Jacobi thetas, I think you define this capital T first, and then you relate it to this var theta. But indeed, it's related because I'm building towards basically this modular form stuff, and this guy is these fancy theta identities you use all of the time when you're studying modular forms. So this kind of theta is a basic building block, if you like, when you're constructing modular forms and modular functions. It's like an Eisenstein series. The Eisenstein series similarly is like a very basic building block that you use to construct other guys. It satisfies all these nice identities.
Yeah.
And
also, the reason that your LaTeX was going weird when you were doing the Z was because you put a lowercase z in the math BV.
That's good to know. Such a function would satisfy. Yeah. Yep, that's a typo. Good. Very nice. Well, all right. I won't bother to re-download the PDF since we're going to not see that probably. Good. Any other thoughts on this little intro stuff. Okay. Now I want to generalize a little bit. So this whole thing basically built up to a function which is defined on a torus. Now I want to generalize a little bit and talk about not a function defined on the torus, one that takes in a point of the torus and spits out some value f of z. I want to talk about functions that take in an entire torus. So this is going to be a little different, but in some sense related. It's more general. So first I want to think about different tori and think about how we can characterize, some coarse data about a given torus. So before I said we could pick two periods, like an omega 1 and an omega 2, and use that to define my parallelogram, and from there the torus. By rotation invariance, you can always rotate the complex plane so one of these guys sits along the real axis, and then if you're allowed to rescale, you can always rescale so that this omega 2 has length 1. So without loss of generality, if I allow rotations and rescalings, I might as well say, all right, well, my torus is characterized by, one period is just going to be 1 on the real axis, and now there's one remaining degree of freedom, which is, we might as well call tau. Before this was omega 2. So there's a shape parameter tau, if you like. This tau now defines some torus because I, do the same thing with the parallelogram and then I identify the sides. Now the claim I want to make is that if we don't care about the overall volume of the torus, but only kind of the shape, if you will, this tau is sometimes called a shape parameter, then sometimes different choices of the parameter tau will lead to the same geometrical torus. The most obvious example is this one over here, where if I, instead of using tau, I use tau plus 1 as my vector, well, this is going to be the same torus because even though the parallelogram looks like it's been squished, all I've really done is added a period, since this 1 is a period. I've added a period to my other lattice vector, so it's really, if you think of kind of physically making the torus, it's really like taking the old torus that we had before, but adding in a twist, right? The torus has 2 cycles, so it's kind of like this blue cycle. It's really like I've used the same cycle, but I've just gone around the torus once when I made that cycle. So it's the same geometrical shape. It's just kind of been twisted in some sense when I'm gluing it together. A slightly more non-trivial one is this S transformation. So this S that sends tau to minus 1 over tau. Well, this actually does change the volume, but if you don't care about the volume, which I can motivate a little bit later why you might not care about the volume, just the shape. If you don't care about the volume, really this tau to minus 1 over tau is just interchanging the two cycles. So it's a little hard to see, but if you imagine that the old torus had this, again, red cycle and this blue cycle, sending tau to minus 1 over tau is really just interchanging them up to a volume rescaling. It's kind of inverting the torus, which interchanges the red and the blue cycles. But again, if you interchange the cycles, that's kind of just like rotating the torus, if you like. If you rotate your head, what looked like, the one cycle is now replaced by the other cycle. So again, up to volume, this should be the same geometrical torus under this equivalence relation we're thinking about. Okay, why would we care? The statement that, well, okay, maybe I'll make the statement on this slide. The statement is that now, if we're going to think about functions that take in an entire torus, we want to think about a function of a torus rather than a function on a torus. You might say, well, we could, if for some reason we don't care about the volumes, you might say, well, a nice symmetry that a function of a torus could have is that the function of a torus only cares about its geometrical shape and not about these kind of equivalent tori that are parameterized by different tau, right? So you might want a function that takes in a torus to be invariant under this class of symmetries, right? Where it only cares about the shape of the torus and not its volume. But the nice thing, of course, about parameterizing our tori by tau is that I can replace this picture equation with an actual equation. I want my function f of tau to be the same as f of minus 1 over tau. So this is another symmetry that a function could have, but I'm now thinking about this in a different way. Before I was thinking about a function on the complex plane that has a symmetry. Now I'm thinking about a function of a torus, although again they're really kind of the same thing, because since tau is an element of the complex plane, this is really a special case of what we were talking about before, because this is a symmetry that a complex function would have. I'm just kind of philosophically thinking about it differently. I'm thinking about it more geometrically. But it's the same thing. It's a function of a complex variable. Okay, fine. So you would say, all right, well, good. You've reduced this to the case we were talking about before, where you have a function on the complex plane that should be morally determined by its values inside some fundamental domain. But now the symmetries are a little weirder looking. This symmetry is not just shifting by a lattice vector. This is a weirder looking symmetry. So you might ask me, what is the analog of the inside of this parallelogram, which has the property that if I know the values of the function everywhere in that domain, then I know it everywhere? The answer is this keyhole region. So this is called the fundamental domain for SL2Z, or the fundamental domain for the modular group. And you can convince yourself that the shaded region here, if you know for a function f of tau, a function of a torus, if you know the values of f of tau inside this keyhole-shaped region, then you know it everywhere else in the upper half plane by some action of these symmetries. So part of that is easy to see, right? Because we have translation by 1. So certainly if I know the keyhole region, I can get anywhere in a shifted keyhole region just by adding or subtracting 1s. The more non-trivial thing to see is that this symmetry where f of minus 1 over tau is the same as f of tau, this does a kind of funny, f of minus 1 over tau, sorry, that. This thing does a weird sort of inversion where it sends this point to a point kind of, I do that a little poorly. I think it sends it to a point down here, if I'm doing this correctly, and then acting with this guy, I think sends it probably to a point down here, and then once you're inside one of these lower regions, you still have your shifts by 1, so I can shift by 1 to go over here, and you can convince yourself if you stare at it long enough that this minus 1 over tau is going to take you down into all of these bubbles. So you can go arbitrarily close to the axis by acting with this transformation over and over. So anyway, yeah, the upshot is that this, I mean, before we had a parallelogram fundamental domain, now we have this little funnier fundamental domain. But for a function of a torus, if I know its values everywhere in the keyhole, then I know it everywhere for the upper half plane. Okay, now let's be a little more precise and not use pictures. So I'll rewrite what I said before. Let's define two symmetry elements. The T transformation is the one that we saw before that shifts you by 1, right? So that was the guy here that it's the same torus because it just twisted one of the cycles. The other transformation is called S. This is the guy that roughly interchanged the two cycles up to a volume rescaling. So it's just changing the A cycle and the B cycle, if you like. Or if you're Greg, you would say it's just interchanging the two generators for pi 1 of the torus, right? Because you just have two cycles that you can route. So it's generated by these two guys, which turn out to commute for the two torus, actually. But anyway, okay. So let's write what I said before. If f is a function that takes in a torus and spits out a number, or equivalently takes in a tau and spits out a number, and it only cares about the overall shape of the torus, not on its, say, volume or if I've rotated or twisted, then f should have these symmetries. These are the same symmetries I just wrote a moment ago. So f should have those properties. And we can say this using the language that we did in the first act. Oh, wait, first I have a challenge for you. Okay, so I'd like to build towards phrasing these symmetries in a more group theoretic way. So we have to ask, okay, what symmetry group does this correspond to? So I'd like to represent it with matrices because that'll turn out to make our life a little easier. So first I'll make a definition that sounds a little unmotivated, and then we'll see why this is useful. So I define a transformation that takes in an integer valued matrix, A, B, C, D, and then acts on a complex number in the following way, and there's a typo. Sorry, that should be tau. The transformation takes in a tau and sends it to this so-called fractional linear transformation, because it's a fraction of two lines. So it sends tau to A tau plus B over C tau plus D. Now, question for you, can you find two choices of matrices? One matrix that implements the T transformation, so it sends Z or tau to Z plus 1 or tau plus 1, and another matrix which implements S. So it sends Z to minus 1 over Z, or tau to minus 1 over tau. So I'll give you a moment to think about that, but it's basically trial and error, so you just give it a try and let me know what you think. Well, we can try to get t, I guess. If t is just supposed to shift by 1. If I want t... Oh, he's typing it in chat. Okay. I see 0, 1, minus 1, 0. Good, because this would be what? It sends tau to just putting in 0 tau plus 1 over minus tau plus 0, which is indeed minus 1 over tau. Good. And the second one is 1, 1, 0, 1. Good, because that sends tau to tau plus 1 over 0 tau plus 1, which is tau plus 1. Good. Very nice. So we have our two generators, which we call T and S. So now, since we have a matrix representation for this symmetry group, it's very nice, because now we can talk about properties in terms of these matrices. So good, T and S generate our group, and maybe I'll do this transformation for you, or this challenge for you. So if we wanted the matrix associated with TST, it would be, well, what? 1, 1, 0, 1 is the T, the S was 0, 1, minus 1, 0, I think, and then this T was 1, 1, 0, 1. So this is kind of some rote exercise, but I'll just do the algebra and probably make a mistake. So this is what? 0, this is 1, this is minus 1, and this one is minus 1 plus 0 is minus 1, if I didn't make any mistakes. And then if I multiply these, I get what? A minus 1. This one is 0, right? This one is minus 1, and this one is 0 plus 1 is 1. I think if I did that correctly,
I think the last one should be -1, because 1 times 0 plus -1 times 0.
Good, good. Yeah, I was confusing myself because I realized the determinant was wrong. Good. All right, so that's right. So why am I doing this? I'm trying to get you to recognize some patterns of the matrices that we wrote down that are not immediately obvious. One is that, okay, well, this guy is certainly still, they're always going to all have integer entries, right? That much is obvious because the integers are closed if I just add and subtract them. The determinant of this guy is still 1 because it's minus 1 times minus 1 and a 0 in the other guy. So the determinant stays 1. And what I'm building to is that this is the group that we've just constructed generated by these two elements is called SL2Z, 2 by 2 matrices with determinant equal to 1 and entries in the integers, which is what this piece was supposed to show you. Okay, and this is actually very easy to prove. So if M is any matrix generated, it's any element of the group generated by these two S and T guys, basically. So M is, some S, N, T, M, S, K, whatever, dot, 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 some numbers of each of these multiplied together. Why is its determinant equal to 1? Well, it's pretty clear. Determinant of M has the property that here it's, it's det S to the power N, det T to the power M. The determinant just splits across when you multiply these guys. Yeah, what you just wrote in chat. Yeah, good. Indeed, so the determinant just multiplies, so all we have to do is check that the two generators, which I've now erased, have determinant 1, but they both did. So this is the determinant condition, that the determinant is always going to stay 1. Okay, so that's the end of that act. The punchline that we just did in a sentence is that we motivated a class of functions that have particular symmetry properties based on this torus picture, and then we defined a symmetry group such that functions that respect this torus property that we said are invariant under a particular group action where the group turned out to be SL2Z, where I just made the belabored point that the determinant stays 1. Okay, last act of this kind of modular forms aside, but any thoughts, comments, death threats, asides, anything? Or more coffee, what do you think? Okay, well, I guess I'll move on then. Okay, so I'm going to motivate what a modular form is. What we said, basically, a function with these properties, I didn't say it, but such a thing is a modular function. So a modular function is a function invariant under the action of the modular group, where the modular group is just SL2Z. This is a modular function. But often in math, and especially in string theory, I mean, if you have some action of a symmetry, the symmetry, sometimes you want a symmetry to hold for a particular class of objects, but it doesn't hold. You get some junk when you act with the symmetry, and then you need to do something to fix the junk. We saw that with the gauge theory last time. So often we have a function that we want to be modular invariant, or you have some physical reasoning for why it should be modular invariant, but it transforms in some more complicated way. And in a very, very broad class of examples, a particular type of junk that you get is, okay, the function is invariant under shifts. That's good. Well, that's a very easy symmetry to have because you could just average over shifts. So your function does have the required periodicity, but sometimes you get a piece of junk when you do the S transformation. So I send z to minus 1 over z, and I don't get f of z back. I get a power of z, z to the k out times f of z. This is kind of like a homogeneous function or something. It's like an overall scaling with some variable when you do the symmetry. So a function with these properties, that it's not quite a modular function because of this junk, z to the k. It's said to be a modular form of weight k. So a modular form has this property where it transforms with a z to the k instead of what it should. But the nice thing about these is that this junk is very easy to fix. If you have a modular form of weight k, you can just multiply it by a modular form of weight minus k, and then you have a nice invariant modular function. So here's an example. This is an example from string theory. It seems a bit unmotivated, so maybe I'll pop over into another book in 1 second. But first, just to say where we're going. In closed string theory, a closed string is just a loop, so it's some loop of string. It propagates in time, so here's time. If you think about the curtain that this guy traces out, this is a two-dimensional shape, right? Because at each time there's a one-dimensional string. So I have a two-dimensional space called the world sheet that the string sweeps out. In string theory, it's often useful, or in physics generally, it's often useful to put time on a circle. So we go to what's called imaginary time. So time is now on a circle, which means that both the string is closed, it's a circle spatially, but I'm also putting my time on a circle. So the topology of the world sheet when I put time on a circle is now a torus. The world sheet is now T2. So I got my T2 world sheet, and I compute a nice physical object called the partition function. The partition function is a generating function for quantities in string theory. Maybe I'll just hop over and sketch the calculation for you. It's not super important to understand the details, but morally what we do is you get, you have your closed string, so you do a particular Fourier expansion where you have some coordinates x, and you say, okay, I can write these as some Fourier coefficients alpha n, maybe e to the in, either sigma or tau, sigma or tau. So you get some Fourier coefficients because it's a string, and then in quantum mechanics, we're instructed to take those Fourier coefficients and promote them to operators on a Hilbert space. So I have a collection of alpha n hats, which are operators on a Hilbert space descending from these alpha n's. And then when I compute my partition function, I'm told to take a particular Hilbert space trace, right? So the trace just means you sum the expectation value of some operator over all basis states in my Hilbert space. So I get some infinite sum that involves these kind of alpha n, which are called oscillators. And the calculation is pretty straightforward. You get some trace that involves these oscillators alpha n, and there's also negative guys. And then you can just write this explicitly. You can write this thing that I'm supposed to be summing explicitly by choosing a basis. This is kind of like a Fock state basis, if you know what a Fock space is. So I write it like this, and then you say, aha, well, in this case, once I've written it explicitly in a basis, the trace is trivial to compute. It's diagonal, so I just add up all of the diagonal elements. So I add up all of those things. It's just the sum of q's to various powers, and then you say, oh, okay, fine, that's a geometric series. That's a sum of q n to the I, which converges to this thing. And then you say, okay, I get one such contribution from each of my set of oscillators. And then when you add up or include all of the contributions from the different oscillators, you have infinitely many of them. It turns into a product, an infinite product over all of the n's of this answer that we got from the geometric sum. So I just do some, some silly math tricks, and I get this answer out, this product. So I was just trying to motivate where this guy comes from, where this product comes from. So this product that comes up in the partition function, you get this funny looking expression. String theory likes to live in 26 dimensions, so there's a 26, then you have to introduce two ghosts that kill off 2, which brings you down to a 24. So you get this guy to the 24th power, but this guy can be written very nicely in terms of the Dedekind eta function. So the Dedekind eta function is this infinite product, and in terms of Dedekind eta, the string partition function, which is the thing that we wanted to compute, or that I told you that I want to compute, it's written very nicely in terms of this eta. Okay, long aside, why am I telling you this? Because this Dedekind eta, which if you're not a number theorist, maybe if you haven't seen it, I mean, you can take as motivation, Dedekind eta comes out of a string theory calculation, as I just showed you. This Dedekind eta is exactly a modular form. It transforms with some junk, right? So in particular, the modular, maybe I'll go back here. In particular, the junk, when I shift eta from tau to -1 over tau, it doesn't quite come back to itself. It comes up to a constant. Forget the constant for now. It comes out with a power tau to the 1/2. Right, so up to this constant, this guy's a modular form of weight 1/2, right? Because if we recall the definition, if you come out with a power of your variable to the k, you're said to be weight k. So Dedekind eta is weight 1/2, is what I'm trying to say. Okay, fine. So the nice thing is that you could have basically guessed this correction, this tau2, if you were given the string partition function, and you knew that it had some products of etas and eta bars, and you knew that that has some junk, that transforms with this power of z to the 1/2, you could have immediately said, aha, if I know the partition function is modular invariant, I could guess that there's a factor here that must have the opposite modular weight, right? So if eta is weight 1/2, eta bar is weight 1/2 in the other direction. So this product is weight 1/2. Or in the other direction, I mean for tau bar, for the conjugate variable. You would say, aha, I know I need to multiply this guy by a modular form with the opposite weight in order to get a modular function. So how would you show that, tau2, for instance, is a modular form with particular weight? Well, it's pretty easy to show. You say, okay, what happens when I send tau to -1 over tau? Well, if I send tau to -1 over tau, I can just multiply top and bottom by the conjugate of the denominator, which gives me this tau1 minus I tau2, and the bottom I get tau1 squared plus tau2 squared. And then I just split the top into two terms. So there's a tau1 over this thing and a tau2 over this thing. So taking square roots, taking the imaginary part. So the left side is tau1 plus I tau2. So now I identify the real and imaginary parts of the left side and see this is, okay, that's how the real and imaginary parts identify under this transformation. So under the S transformation, tau1 goes to this and tau2 goes to this, is what I'm trying to say. So if tau2 goes to this, that means root tau2 goes to the root of that quantity. But that thing you could rewrite as root tau2 times the norm, tau bar, to the power -1/2, right? Because tau bar is tau1 squared plus tau2 squared, and it appears in the bottom with a root. So this is the proof that the imaginary part of the variable transforms as a modular form with weight -1/2. And that exactly cancels the eta. So the upshot of all of this is that you can, when you do these calculations, you have an analog of, dimensional analysis somehow, a sanity check. In physics, we use dimensional analysis to immediately check whether a formula is correct, or to guess the formula. If you know the dimensions it has to have. Here we have dimensional analysis where the dimension is the weight of your modular form, right? You have to have modular forms of opposite weights if you know that they multiply to a nice physical modular invariant quantity. Good. Okay, this is what I basically just said. So, yeah, this, as I was saying, eta transforms in a particular way with this junk. It does this thing. It's a modular form of known weight, and that means that the tau2 comes in and saves the day so that this product is modular invariant. Kills this bad stuff. Okay, so that's the last part of the modular forms talk, and then maybe in the last little bit I'll jump back and tell you why this modular form is related to the simplest case of Langlands. But maybe I'll stop if there's any questions about the punchline that, eta is a nice modular form and you can combine it to get modular functions. Any thoughts or comments on that stuff? Okay, no thoughts. One question you could ask, I'll put words in your mouth. One question you could ask is, why are you saying the volume of the torus shouldn't matter, right? You claim that this is some physical property, this partition function, which is modular invariant, but modular invariance assumes we don't care about the volume of the torus, only its shape. That sounds very unphysical, you might say, right? Why do you think in a physics context you shouldn't care about the volume of the torus? And the answer is that string theory is a conformal field theory. Conformal means it's invariant under rescalings and local kind of rescalings of the metric. And conformal field theories don't care about volumes, which is why the torus doesn't. And maybe just one quick aside that in any conformal field theory, the partition function will be modular invariant. You could ask, are there other field theories that are not conformal but still modular invariant? And the answer is very interesting. Under some mild assumptions, if you assume you have a one-parameter family of theories such that they're connected to a conformal field theory at one endpoint, and make some other mild assumptions, but you assume in particular that the theories remain modular invariant. So morally, they only care about the shape of the torus and not its volume. There is a unique one-parameter family with that property, and it's called the TT-bar deformation. The TT-bar deformation is roughly the unique deformation of a CFT that maintains modular invariance of the partition function. And the proof of that is very elegant. You basically do something similar to what we did in the gauge theory talk, where again, in the gauge theory talk, we said the naive derivative was bad because it introduced some junk. You make a modular covariant derivative. This is now a derivative on the complex plane. It's not the derivative with respect to the complex parameter tau, but it has a second piece that subtracts off some junk. And then you use this gadget, this modular covariant derivative, to prove that a TT-bar deformed field theory still has this SL2Z symmetry, which is remarkable. I mean, there's no reason you should expect an SL2Z symmetry for a theory that, is not scale invariant. It should care about the torus volume, you would think. That's very surprising. Okay, last part. I spent this long aside telling you about this third part because modular forms I claimed were useful for Langlands. So let me explicitly show you how 2 and 3 connect, and then I'll say nothing about the fundamental groups of Riemann surfaces. Maybe Tetra can talk about that or something, because he's our local expert. All right, so I'm going to speed run this because a lot of this was pitched at a level that was too elementary for the audience. But the motivation I gave at the beginning was that the Langlands program, in its simplest form, let us solve Fermat's theorem. So, as you know, there's plenty of solutions for Pythagorean triples. If you restrict that they have to be integers, they form this this interesting plane geometry. There's the conjecture from Fermat that there's no solutions when n is greater than 2, and the proof required introducing this Langlands type stuff. As I told you, it relied crucially on the Shimura-Taniyami-Vey conjecture. So what was the technology I told you we needed to prove Fermat's theorem? I said this conjecture related cubics to the solutions of equations over Fp. I'm basically going to skip this entire act because I assume the audience knows what Fp is, but if you don't, the motivation is just to think about integers mod n, right, like clock arithmetic. So you identify 12 with 0, and you add two numbers. You just subtract 12 until it lies back in the range from 0 to 11 again. So this is, if you like, kind of like degrees. It's arithmetic modulo 360. If you add 2 degrees, it's equivalent to some other number that lies within the range from 0 to 360. There's some nice properties of arithmetic in mod n. Addition and multiplication work the way you would think, but division doesn't. Division is not preserved. So this property turns out to be false. Also, if you work in the integers mod n for some arbitrary n, it might turn out that some numbers don't have multiplicative inverses. You can just look at the multiplication table and see there exists no number in arithmetic mod 4 that is somehow the multiplicative inverse of 2, which means you can't divide. That's kind of bad. You can't divide in the integers mod n for general n because some numbers won't have multiplicative inverses. And then I had a challenge where you do this mod 5 and check that for the integers mod 5, everybody does have an inverse. And then I eventually tell you, if you didn't already know, that you always have inverses if and only if you're working in the integers mod p, where p is a prime. So the upshot of that, Greg proved this in a video, I think, in his abstract algebra sequence or something like that. So you can look there or in a book if you want the proof. But the point is that if you want to be able to divide, you need integers mod n where n is a prime. So in that case, I write it like this, fp. Okay, here's the key insight that one uses in this proof for Fermat's last theorem. You say, okay, rather than studying solutions in the integers, I want to look for properties of the solutions in a finite field, f sub p. So for instance, when you work mod 5, this equation does have some solutions, this cubic equation that doesn't have solutions in the integers. If you work mod 5, you can check that if you plug in, say, 230, you get this thing which adds up to 35, which is 0 mod 5. So that's equal to z cubed, where z is 0. So, okay, this is a strange thing to do. You might say, how is this going to help us? Well, if you delay gratification for a moment, it'll turn out that the interesting data comes from counting the numbers of solutions in the field fp as a function of p. So I have an infinite sequence of numbers, a sub p, that encode the number of solutions to this equation mod p. So let's see. That was a rapid... yeah, okay. After this, I think I just get to why Langlands is solved by doing this thing. But, okay. There's a brief kind of conceptual leap between going from this particular solution, or this particular equation, the Fermat type equation, to a cubic. I didn't really motivate this. I jumped from talking about Fermat to talking about cubics. But as it turns out, when you prove Fermat's last theorem, there's an intermediate step where you use the solution to the xn plus yn equals zn type guide to construct a cubic or an elliptic curve, this sort of thing. So I will gloss over that entirely. But now I'm just going to shift focus and say, okay, now instead of Fermat, we're going to look at cubics because there's a way to go from the Fermat type polynomial to a cubic. Okay, so now I'm going to look at cubics, in particular of this form. And I'm going to focus on, as a very concrete example, this cubic. So this is some polynomial in y and x that goes up to x cubed. And I put in an x squared, whatever. It's not that important. This thing generates some elliptic curve. The challenge, which I will not ask you to go through since it's a bit tedious just checking solutions, you can work mod 5 and find some solutions that satisfy this equation, and you can list them. I think I list them here. Yeah, I write a little Python program to list them. So if I define a function that is the cubic I just described, and then define a function that gets solutions by just stupidly iterating over all possible pairs, and then checking whether the equation is satisfied. If it is, I append it to some list, and then I just return that list. So for that particular cubic mod 5, there happen to be 4 solutions, these 4 that are printed out at the bottom. Okay, so we can repeat this procedure for different p. And what you would find if you did this as an exercise is that if you look and count the number of solutions to that particular cubic mod p, they roughly grow like p. So the number of solutions is kind of like scattered around a line that's roughly growing like p, but not exactly. There's some scatter around that line. So you would say, okay, well, since they roughly grow like p, let me subtract p minus the number of solutions to remove this asymptotic behavior. So I define these called p deficits. The p deficits a sub p are just the difference between p and the number of solutions to that cubic mod p. So in the previous slide, there were 4 solutions when p equals 5. So the deficit there is p minus 4, which is 1. And now you say, okay, whenever I have a nice sequence of integers, it's often useful to encode them in a generating function. So I'll define a generating function that's just, it's a bag for holding all of these integers. I put all of the AP into this function. So it's just a formal power series in some variable q that encodes all of these interesting numbers AP. Okay, at this point, you're probably thinking, okay, what could this possibly, where could this possibly be going? You're doing a very strange sort of procedure where you define these numbers a sub n by taking the difference p minus the number of solutions to a particular cubic equation that you wrote down, and you're trying to solve it in the fields f sub p, finite fields, and then you get some random junk, right? It looks like there should be no pattern here. It's just a collection of integers on the primes, indexed by the primes, that it's dubious whether they have any structure whatsoever. So you would be right to be skeptical at this point. But as it turns out, I'm going to skip this. As it turns out, if you study this function, f of q, who has the property that its expansion coefficients on all of the prime numbers, I don't care what happens on the non-primes, right? It can do whatever it wants there. I want to find a function f of q that generates all of those deficits to this weird cubic equation. So all of the expansion coefficients match these p deficits on the primes. It turns out that that function is very familiar. That function f of q, whose Taylor coefficients give us those deficits to the solution to that cubic, happens to be a product of Dedekind etas. So this exact eta function that came up in string theory when you compute the string partition function miraculously appears in this number theoretic question of how many solutions does a cubic equation have working in the integers mod p. Eta appears there in exactly the same way. And as we learned in the previous part, eta is one of these modular forms, right? It transforms with weight 1/2. So there's a modular form whose Fourier coefficients count the number of solutions to this equation mod p. This is remarkable. To me, this is a mind-blowing moment. So this was proven by Eichler in 1954. You can see his paper for the proof. But this is the big mind-blowing moment, for me at least, that Dedekind eta shows up here. Okay, so to conclude, I had some challenges baked in here where we verified some of those terms, which I don't really want to do for you. I'll just tell you, you can write a function in Mathematica and just check it up to whatever order you want. Here I check it up to order 23. But the product of the etas exactly matches the numbers that we got before. Now I'll just tell you the main result. So what did we just find? And we found that if you look for solutions to a cubic in FP and count some stuff, those counts are encoded in a generating function, which happens to be a modular form of weight 2, right? Because I have a product of 4 etas, each eta is weight 1/2. So it's a weight 2 modular form. Here's the big theorem. Any elliptic curve you could write down any equation of the form that I wrote before, and try to find solutions in the integers and compute the deficits in this way. Any such elliptic curve will give you some coefficients a sub p that are the Fourier coefficients for a function with this property. It's a modular form of weight 2. So this is amazing. I mean, any cubic equation is associated. There's a one-to-one correspondence, basically, between cubic equations and modular forms. In this case, with weight 2. Okay, so this is already remarkable, but just to conclude by reminding you of what I said at the beginning, the proof of Fermat's last theorem uses this exact conjecture. So one more time, the proof is that you start with the assumption that there exists a solution to the Fermat type equation. You use that solution to construct a cubic. You count the solutions to that cubic in FP, and then you demonstrate that those counts cannot be the Fourier coefficients of a weight 2 modular form, which contradicts this modularity theorem. So the contradiction here is the proof that Wiles used in proving Fermat's last theorem. That's the answer. So that's the end of the whirlwind tour. So I've just shown you that studying modular forms is somehow related to number theory solutions to this thing, and I'll just briefly comment that this thing can be generalized. So that's the beginning of Langlands. Modern Langlands doesn't just study solutions over finite fields. It turns out that those counts a sub p, they're related in a natural way to two-dimensional representations of the Galois group of the polynomial that you wrote down. So you can actually abstract away anything about solving equations mod p. You can just look at group theory, Galois theory, the representation theory of the Galois group. So that's a generalization here. In part 3, you can generalize from going to modular forms to automorphic forms, which have more complicated symmetry groups than just SL2Z. And then I'll said almost nothing about this, but there's a third correspondence, again, that relates the data in 2 and 3 to the properties of the fundamental group of some complex surface. And this thing generalizes as well. I think eventually when you generalize it, you have to replace automorphic functions with the sheaf of functions, the appropriate sheaf instead. So there's a sheafification of this story that Drinfeld did, Vladimir Drinfeld, who's a professor here at UChicago. And I think if I remember correctly, it was 1980 or somewhere around there. Drinfeld came up with this sheafification that is, I think it's called geometric Langlands, that generalized this even further. But that's a story for another day. Okay, I've gone already 6 minutes over the target of an hour, so I will stop here for questions, discussion, or death threats. All right. See ya. Thanks for coming. E-trippy.
You know that slide 22?
Slide
thing?
22. This thing, yeah.
Yeah, is there like a string theoretic interpretation of this theorem?
Good question. If there is, I don't know of it offhand. I know people have worked on this on number theoretic connections with string worldsheet calculations. That's a very good question. I probably should know this, but I don't know offhand how you're supposed to think of this string theoretically. I guess it would tell you that there should be some correspondence between cubics and string partition functions, or at least modular and variance on the world sheet. That's a good question. Yeah, I'll look that up, and if I find anything, I can let you know.
Yeah. Okay.
Good. Other thoughts or number theorist rantings or anything like that? If not, I will stop.